So the rows of the diagram were some abstract chain complexes. So it's a sequence of abelian groups and their maps between them. So that the composition of any two maps is trivial. We have a second chain complex B, which has its own maps D. And we consider there can be a situation where, okay, we have, for example, just a pair of chain complexes, and sorry, here n-1, of course. And there is some map between the corresponding pairs of the abelian groups with fixed index. For example, if we have just this situation, so let me remind you, if we have just this kind of setup where we have a pair of chain complexes and we have a bunch of maps I between the corresponding groups with fixed degree, by degree meaning this index here. And if this is a commutative diagram, such collection of maps I is called a chain map. Particularly, what is good about such situation is that okay, for both of these chain complexes, you can define homology theory. So in each degree, the homology is just a quotient of the kernel of this D modulo the image of D. And once you have, if you have this chain map, so this is commutative, you can define the induced map on the homology groups. It's well defined. And then we consider it a kind of a special case when we have also a third chain complex C. Then the bunch of maps from the B groups to C groups, which is denoted by J. And we require that now the columns actually, they form short exact sequences. Each column is a short exact sequence. Which in particular tells you that each of these I maps is injective, each of the J's is surjective, and moreover, at each place here, the kernel of J is equal to the image of I. And this is a situation, this kind of setup we called exact short exact sequence of chain complexes. Okay. Cover such setup, and then we wanted to define. So our goal is to consider, show that this in this situation like this we have a long exact sequence of the corresponding homology groups, namely for the nth homology group of the complex A, we have induced map I star to the nth homology group of the complex B, and then similarly we have J star, which maps us to. But then there will be a map between Hn of C and Hn minus 1 of A. And then we repeat what we had before, but with index shifted by 1. So one of our goals is to construct this map delta, and the other goal is to check that this indeed will be a long exact sequence. First, we need to define this delta map. So delta, well, sometimes called a connecting homomorphism. Connects these parts of this long exact sequence. It's homomorphism from abelian group Hn of C to the abelian group H minus 1 of A. And okay, we want to define like some class in this group gamma, group Hn of C, and we want to say where does it go. So gamma should be, so it's a representative of some class in homology group in degree n, so it should be an element of our group Cn such that it's in the kernel of our D, such that D gamma is 0. We have to, so if you look at this huge diagram which we have, so let me we have a gamma living in this place, in this here. Sorry. Right, and because it represents some element in homology, it's some element Cn. We want to construct some something in the again, sorry, nobody corrected me because yeah, my degrees went in the wrong order. Of course, in the chain complex, the degree is decreasing. We need to obtain some element in the homology of our chain complex A in degree n minus 1. We need to obtain some element alpha here. And so we have to somehow try to go along this diagram to obtain alpha. Well, the naive way is just to try to find some preimage, like first try to find a preimage of gamma under this map, and this beta. The beta is mapped to gamma. Then take our beta here by just acting by this D map to take as D beta, and then try to find some preimage of this D beta with respect to our I map. And this preimage will give us some element alpha here. So namely, when we define map, this gamma, class of gamma, will be sent to class of alpha, such that alpha satisfies the following, such that alpha is determined by the following, essentially determined by the following system of equations. So J, so first, there's the equation that gamma is J of beta. And the second equation is that I of alpha is equal to D of beta, which essentially tells us, the first equation tells us that beta is a preimage of gamma under this vertical map, and alpha is a preimage of D beta under this vertical map I. This is what we want, but of course, there are a lot of questions about, okay, we can try to define like this. There are a lot of questions about this. Okay, first, does this system always have a solution? Can we always find these preimages? And there seems to be, well, the preimages can be non-unique. You have to take preimage at two places. At each of these places, the preimage can be non-unique. But what is if you take other preimages? So would the result be the same or different? So there are a lot of things you have to check that under all these choices you would have to make the result as the homology class of alpha would be still the same. Okay, this is what we need to do. We formulate the following remark. This delta is well defined. The first question, indeed, we want to ask a question, does it actually exist? There exists alpha such that this system so let me kind of schematically keep this diagram in mind. Here, I mean, you can always, again, this is the rows, our chain complexes, and the columns are short exact sequences of abelian groups. So here we have some sort of, we start with gamma here, then the beta here, the beta here. Related by J, this is by D, and here is I. So first, we notice that this, we use the fact, let's remember that at each column we had short exact sequence. In particular, these J's are all surjective. So J is surjective. This means they always exist. This can always be solved for any gamma. Beta such that J of beta equals gamma. So at least this equation we can always solve. Good. And now, well, gamma was an element in our homology. So in particular, we know that in order for gamma to represent some element homology, it's D should be 0. So the D map should take us to 0, this horizontal map. And well, this means that D, so for gamma, we already know that there is a B such that gamma is J of B. So in particular, this means that D of J of B is 0. Okay, J and D, so J is a chain map, so J commutes with D, so we can write it equivalently as J of D beta is 0. But then this means that D beta is in the kernel of J. But this implies, since we know that kernel of J is always, essentially means that here D beta is also set to 0. This is just essentially follows from the commutativity of this square. And since D beta is sent to 0 under J, and we know that these the columns are short exact, the kernel of J is the same as image of I. Kernel of J is equal to image of I. This means that D beta is in the image, and this means there indeed exists some alpha such that I of alpha is equal to beta. Filled by J, there is necessarily in the image of some element here. Okay, so this proves existence of the solution to this system. And now we have to check that the map is well defined, so it's independent on the choices we will make. Second point we will check is that let's consider that we take beta prime instead of b. Beta, such that this beta prime is another solution of this first equation. Of gamma here, beta and alpha, but we can take another preimage under J, beta prime. And there will be correspondingly another different d beta prime and possibly another alpha prime. Right? Alpha prime will be such that I of alpha prime is equal to beta prime. And we want to check that the result as an element in the homology will be the same. So we want to check that this alpha and alpha prime represent the same class in homology. Okay, let's consider J of this difference, beta and beta prime. So we know, so by definition, the image under J is the same, so the J of the difference would be 0, right? So, because J is a homomorphism between abelian groups. So this means that beta prime minus beta is in the kernel J. So this difference is killed on this map. And again, we know that the kernel of J is the same as image of I, because this is here we have a short exact sequence. And this means that there exists omega here such that I of this omega gives me this difference. Since the difference is killed by J. Okay, and then let's consider I of alpha prime. I of alpha prime is, well, by construction is d of beta prime. But from the other hand, we can express beta prime using this equality. So d of beta prime is the same as d of beta plus I omega. This I omega is the difference between beta prime and beta, which we constructed. And then we use linearity. This is d of beta plus d of I omega. So again, I is a chain map, so it commutes with d. It's the same as, and d of beta is, we know it satisfies this equation that it's image of alpha. So this is the first term is I of alpha as before. And here we have, we can permute d and I. So this is the same as I of d of omega. And then we can use that I is a homomorphism, so I of the sum is the sum of I, so this is the same as I of alpha plus d omega. So we show that I of alpha prime is the same as I of alpha plus d of our omega. But we know that I is injective. And this implies that alpha prime must be equal to alpha plus d omega. But that tells us that indeed there is the same in the homology, because in the homology we factor out the image of D. This tells us that the resulting class is the same. Okay. So this we check that. So we check that choosing a different image of gamma with respect to J, so choosing beta prime instead of beta, results in the same result. Of course, we don't have to check, like for fixed beta, we don't have to check that there exist different preimages under this map, because we will know that I is injective. So once we fix beta, the alpha is uniquely determined. So this part we don't have to check, but we still have to check the following, that the map is, we only define this map on homology. So we can actually, the other thing we can do is choose a different gamma. So different gamma which represents the same class in homology. This is what we still need to check. Let us take gamma prime instead of gamma such that they have the same class in our homology. Well, what does this mean? This means that by definition they differ by d of something. And if you look at this schematic mini version of our diagram, so we have gamma here, which we lift beta, then we have d beta here and alpha. And now we take another gamma prime here, and so that the difference the preimage of the difference under this D map is some eta. Here. Okay, and now let's use, so we know that these maps here are surjective. Remind you, these maps are injective and these maps are surjective in our setup. So J is surjective. So in particular, we can always find the preimage of this eta. Exists mu such that J of mu equals eta. Okay. Let's use this. So our gamma prime is equal to gamma plus then. So explicitly write eta in terms of this mu in this equation. And again, we can commute J and D by writing this as we can commute D and J, and we also can use the fact that for gamma we also have a preimage. We already have a preimage with respect to this map J. which is beta. So this is J of our beta. So the whole thing can be written, and also we can mute J and D here, and we can write this bilinearity as J of beta plus mu. And this means that essentially, this tells us that once we changed this gamma instead of to gamma prime, this is equivalent to changing beta, its preimage, to beta plus d mu. So our new, this means that it's beta prime, where preimage of gamma prime is the same as beta plus mu. Mu under this horizontal map is mapped to the difference between beta and beta prime. So mu is preimage of the difference beta and beta prime. And okay, so but we need to check how alpha changes here. So our original alpha was determined by this equation that it was preimage of beta, preimage of d beta. And so here we have d beta prime as well, and it will have some preimage alpha prime. I alpha prime is d of beta prime. And now we use the fact that the beta prime, we know the difference between beta prime and beta is given by d mu. This is the same as d of beta plus d mu. But d composed with d is 0, so this is the same as d beta. So we arrived at the fact that I of alpha is the same as I of alpha prime, but we also know that I is injective. Means that alpha prime is the same as alpha. So in this case, well, we changed gamma to gamma prime, but this at the end, this alpha prime is actually just the same. The result is not modified. So we can collect these all three checks together to conclude that indeed this delta is well defined. Any questions? All these kind of techniques of proving things, sometimes called commutative diagram chasing, to kind of chase some elements along here. Okay, now we want to prove the following very important theorem. This theorem will allow us to calculate essentially homology groups in many examples. That sequence, so the following long exact sequence. And you start with HN, A, and B. Here you use, again, we are assuming the same setup. Here's a setup where we have this short exact sequence of chain complexes A, B, and C. Then the J star takes us to Hn of C. Then we use this map, which we worked hard to show its existence and we'll define it as delta, which takes us to Hn minus 1 of A. And then we continue as before, but with grading shift by 1. Because this actually comes also from delta. Okay, sorry. Now, if I formulate it like this, this will be tautological. The long sequence like this is exact. This is what we want to show. We know all these maps, but we have to check that they satisfy the condition of exactness. We want to check that each point here, the kernel of the next map is equal to the image of the previous one. We have to check exactness here, here, and here, or equivalently here. It doesn't matter. 3 places. Okay. And this will require, again, some work of a similar nature of this diagram chasing. Okay, we'll start with something easy. At this place, so this place doesn't involve any of this delta map, which is relatively complicated. So in this place, to show exactness at this place, we have to check that the kernel of J star is equal to the image I star. Okay, this is just one. Let's use this notation. And here we will split kind of the proof of equality between. There should be equality of some subgroups here, and we can split it by kind of show equality by first showing equality, certain inclusion in one direction and then inclusion in the other direction. So let's first check inclusion. So this is the easiest to do, the inclusion of the image of I star into the kernel of J star. Well, this is easy. Okay, we know that the I and J themselves, they formed the short exact sequence. So this composition of chain maps was 0. And this implies automatically that composition of the induced maps on the homology groups is also 0. So this means if you apply this to anything, this will imply that all elements in the image of I star will be automatically killed by J star. So this will imply indeed this inclusion. This was easy, but well, the rest won't be so easy. What about inclusion in the other directions? I want to check that the kernel of J star is included in the image I star. Okay, let's take some element in this kernel represented by some beta, and let's check that it's indeed actually in the image of I star. let's keep in mind schematic version of our huge commutative diagram. So beta, so kernel, so J, so the J maps like this, I maps this, and here we're considering so we're considering this beta representing some element in the homology of the complex beta. So some element, for example, here in the homology of complex B. B is some element, and we know it's in the kernel of J, so it's under this J map, it's just sent to 0. Sorry, no, it was fast. Regard this. So yeah, we know that the class of beta is in the kernel of J. This means that it's scaled by J star 0. But what is the definition of J star? The definition of J star is that we take, to calculate J star of this class of beta, we take a class of J of beta. And this is 0. So J but this is equivalent to saying that J, so this gives a trivial element in homology. This means it's D of something. Let's say D of gamma. Here. For some gamma. Okay, good. And now we use the fact that this J map is surjective. So this gamma has some, we can always find a preimage of this gamma. So J is surjective. For any gamma, there exists mu, such that gamma is mu. J is surjective, we can find this preimage. And then let's consider J of the difference between beta and d mu. So what we are having here, we started with beta, we transfer it to here, J of beta, then we found preimage, again preimage, but then we want to send essentially mu back to this place. Using just directly this D map. So this mu at this place. And so we obtain something here. And then consider what kind of the difference. Let's see, so this is D mu, but we also have beta at this place. Then we can consider the difference between these two guys and send the difference by J again downstairs. So namely, we're calculating J of beta minus d mu, which is, okay, J of beta is by construction was d of gamma, right? Yes, gamma was a preimage of J of beta under d. And here we have, we can commute D and J of J of mu. And then, but J of mu by construction is also gamma. This is D of gamma minus D of gamma, which is 0. Essentially follows, it follows kind of, it automatically 0 essentially because this square is commutative. So if you kind of constructed some preimage by going in this direction and then you send it back here, you necessarily should get the same stuff. So this is why the difference between these two guys is automatically sent to 0, but more explicitly you just check it by this by formulas like this. Okay, and so J of this difference of d mu, d mu and beta. So J of the difference is sent to 0, but this means that beta minus d mu in the kernel J, which we know is the same as image of I. So since the difference is killed, we can find its preimage here. Say alpha. There exists alpha such that beta minus d mu I alpha. Okay. And okay, this alpha essentially we will use. The idea is that to use this alpha to show that it will represent a class which is a preimage of this beta under I star. And this will show that this class of beta is indeed in the image of I star. So how exactly does this work? Well, let's first consider I of d of alpha. So this is the same as d of I of alpha. But by construction, I of alpha is this difference between beta and d mu, which is d squared is 0, and here we have d beta, which is must be 0 because beta represented some element in the homology. Okay, if I of d alpha is 0 and I is injective, this implies that d alpha is 0. And this in particular means that alpha now can be used to define a certain class homology of our complex A here. It's killed by D. And okay, good. And moreover, okay, now I can apply I star to this class of alpha, which is by definition of the induced map is the same as class of I of alpha, which is, and I of alpha is again this difference. And d mu is killed in homology. So this class is the same as class of beta. We find, so all this hard work which we did was to find this, indeed this some element which is some element alpha who represents a class such that if I apply I star on it, I'll get beta. So this shows that our beta is indeed, the class of beta is in the image of I star. And by construction, so which was the class of beta was arbitrary element in the kernel of J star. So this implies that indeed the kernel of J star is included in the image. So we checked, again, we checked inclusion in both ways. So combining this 1a and 1b we show that indeed the kernel of J star is equal to I star. So this shows exactness. One of this place exactly shows exactness place. And now we will check exactness here. We want to check that the kernel of delta is equal to the image of J star. Any questions so far? This is what we will do. Again, we'll split it into two steps. So first step, we want to check inclusion of the image in the kernel. Okay, to do this, again, take some arbitrary class represented by gamma in the image and show that it's in the kernel. So we need to show that it will be killed by delta. Again, so let me diagram here, and gamma lives here. Okay. And we know that gamma represents element in homology, so it's killed by D. And so it's in the image of J star. This means there exists mu here such that gamma is J star of this class of mu. J star of the class of mu is the same as the class of G of mu. And we can just choose, since gamma, any element representing a given class, you can always just choose gamma to be equal to J of mu. So we choose, without of loss of generality, choose gamma just equal mu. Now, let's consider. So we need to check that this gamma is in the kernel of delta. So let's apply delta to this class of gamma, and by construction, it gives us some class of some element alpha, which again determined by this system of equations. So remind you, so to determine this, the result of delta, we found first some beta here, which was a preimage of gamma, and then we applied d, and then we found alpha, which was preimage of this d beta. But then, so we needed to solve this system of equations. Gamma equals j of beta, and d beta alpha. But of course, okay, beta in this one, when we find this alpha, okay, beta was preimage of gamma under this J map. But we already have some preimage, which is denoted by mu. So we can just take our beta to be mu. So we can take beta. Take them the same. Loss of generality. Because as it showed, it doesn't matter, we can take any preimage. Okay, then let's see. So what about so I of alpha? Okay, I of alpha is, gives us d beta by construction, which is the same as d mu. But we know that mu actually represented some element in the homology. This means that d mu was necessarily 0. This is 0. And we know that I is injective. So then I of alpha equals 0 implies that alpha is 0. Alpha is 0, and therefore its class is also necessarily 0. This means that delta of gamma is indeed 0. And this indeed verifies this inclusion. So we check that an arbitrary element in the image of J star is killed by delta. Now I want to check inclusion in a different direction. The kernel of delta is inside image J star. Okay, so now let's take some element in the kernel, and then we'll find its preimage under J star. Gamma is somewhere here, and so we know, okay, so this the delta of gamma, which again is just defined as a class of alpha reconstructed by this sequence of preimages. So first we construct beta preimage here, then we act on it by d, and then we find preimage alpha here. But we know that this should be a 0. The class of alpha should be 0. And this means that alpha is d of mu for some mu. Means there exists a preimage of alpha on the D map here at this place. Okay, and so what about, so we know that, okay, so by construction, d beta is I of alpha, I map. And now we can explicitly write alpha as d mu. So this is I of d mu. And again, we can exchange and I like this. And we can rewrite this equality in a way that the d of beta minus I of mu is 0, using linearity. In other words, you can then map this mu to I of mu here. And the statement that the result will be, the difference between these two guys will be killed under D, which is, again essentially follows from the fact that this square is commutative. But more explicitly in formulas, we showed it here. Okay, and then, well, let's use this difference and act on it by J. J of this difference is the same as J of beta. This is because composition of I with J is trivial. This is because this, by our setup, the kernel of J is equal to the image of I, and J of beta is gamma. I of mu is automatically sent to 0 here. The difference between these two guys is also sent to gamma. And this in particular implies, so why did we need this mu? Because we wanted to construct element, we want to construct some element of homology so that J star of it will give us this gamma. So beta, so naively we can try to use beta, but beta is not doesn't represent element in homology because D is generally can be non-zero, so it's some D beta. But we can kind of track this d beta like this back here to some I of mu, so that this difference is actually killed. So the difference itself is this difference does represent an element in homology, and in particular, so if you look, so this is killed by D. So by looking at the equality gamma equals to this, we can conclude that the class of gamma is equal to the class of J applied to beta minus I of mu. And this is the same by definition as J star applied to beta minus. This is valid thing to consider because this is killed by D. And indeed, we found some element, so the J star of it gives us gamma. So we check that this gamma is necessarily inside the image. Okay, so combining this to A and B, we conclude indeed that the kernel of delta is equal to the image of J star. So we checked exactness at the second place here. And finally, we need to check exactness here or equivalently here, it doesn't matter, you just shift of n. So we need to check that the kernel of I star is equal to the image of delta. third place. Check the exactness of the sequence is at the kernel of I star of delta. And again, we will show first inclusion in one direction, then inclusion in the other direction. So let us start showing that image of delta is inside the kernel I star. Okay, and so as usual, let's let's take some something in the image of delta. So this is delta necessarily of this form, delta of something. Which again, so you by this time you should be already familiar. So to calculate this delta, we first find preimage beta here, then we apply D, and then we find preimage alpha here. And so okay, we take some arbitrary element of the image, and we want to check that its kernel is killed by I star. So let's do this. So we apply I star on the element of this form. Okay, by construction, by the definition of this delta map, this is a class of alpha, which we find here. And okay, but then this is by definition of this I star, this is the same as a class of I applied to alpha. But this I applied to alpha, it gives us beta. And but D of something is trivial in homology, so it's 0. So this was relatively easy compared to other cases. And okay, the last step to finish the proof of this theorem is to show inclusion in the other direction. (3b). Check that image of delta contains kernel I star. Okay. Let's take class, some homologic class represented by alpha in this kernel. This is alpha will sit somewhere here in this first row. I okay, it's in the kernel of I star, meaning that I star applied to alpha is 0, and by definition this is a class of I alpha. And this implies, so the fact that this is 0 implies that I of alpha is D of something, call it eta. Here you have I of alpha. And we know that it's killed by D. Sorry, no, we don't know this. What we know is that we do know this, but we know that it's a D of something, right? It's trivial in homology. This means there exists a preimage here, which we denote by eta. Okay, good. And then let's. Okay, we can first actually we can move this eta. We can apply J, this map here, to obtain J of eta here. And then we see that if you kind of consider like this by kind of construction, this alpha satisfies the definition of delta applied to the class of J of eta, right? Because alpha, so eta is a preimage under this map, and then we apply D, and then we take preimage here. So by the definition of this delta, the delta applied to the class of G of eta is a class of our alpha. Okay, what about, well, you have to be, okay. One thing one has to check, of course, is that, okay, delta was defined on the elements of homology. So we have to check, before saying this, we actually have to check that this J of eta actually represents some element in homology. So we need to check that D kills G of eta. But let's see what is D of J of eta. This is the same as J of D of eta, which is J of D of eta is I of alpha, J of I of alpha, but this is 0 because the composition of I and J is trivial. This is indeed okay, and indeed J of eta defines some element in homology, and its class by the map of delta is sent to the class of alpha. Well, okay, we are done because this is what we wanted to show, right? We started with some arbitrary class in the kernel of I star, and we show that it's a D of something. And this finally concludes the proof of this, the long proof of the theorem about long exact sequence. Okay, so this was a lot of algebra. You might ask, why do we care? Okay, let's now we can return to topology. Again, this this setup where we have a so when you consider it, the notion of relative chain complex, we had a particular case of this setup where we have a short exact sequence triple of chain complexes. Namely, we can formulate this as the following corollary of the theorem, which immediately follows by taking this general statement with AN groups being, again, this, I'm a bit abusing this notation A. So A, now we return to our setting where we have topological space X and a subspace A inside. So AN, in this general setting, we put groups AN to be groups of chains, singular chains in this space A. BN will be chains X, and Cn will be our relative chains. The quotient of Cn of X with respect to Cn of A under our inclusion. And this quotient we also denoted as Cn of X, comma A. And we have the maps here. So this is our, so what was the, well, we can just, so in this case, the map I here, inclusion. We have a canonical conclusion of chains in subspace A into X, and here this is a canonical J will be our projection quotient map. And so we know that indeed this is injective, this is surjective, and the kernel of J is exactly image of I. Okay, so this is indeed provides us an example of short exact sequence of chain complexes. So I'm just repeating what we already considered before. Just a reminder. And fit it into a short sequence like this. So from the theorem, then we have the following statement that we have a long exact sequence of our homology groups like this. So we take Hn of A by this I star sent to Hn of X, which is by J star is sent to relative homology group Hn X comma A, and then we have this connecting homomorphism delta, which takes us to Hn minus 1 of A, and then we repeat. And the statement that this is exact. So let's see how can we, for example, use this. Well, let me say a couple of few words in general. So in general, so this the fact that this sequence is exact, it can be very restrictive. So in particular, if you know, in general, if you know some elements, some groups in this exact sequence, this can constrain sometimes completely what are other groups in this sequence. In particular, like if you know the homology of A, homology groups of X, this often can help. The fact that this is exact can always tell you what are these relative groups, or the other way around. So let us consider a very simple situation where you always kind of universal example where, well, in the sense that it can be for any space in the following sense. For any space, logical space X, you can consider one point. There always one point subspace. You just take a subspace containing some single point X. Okay, how does this long exact sequence? So we know the homology groups of a point is Z when n equals 0 and trivial otherwise. So this tells us that kind of this long exact sequence will look differently for n around n equals 0 in the beginning and for general one. So suppose first, consider first the case when n is considering strictly greater than 1. So, and we consider the part of this long exact sequence. So this is A, which looks like this. So Hn, we have Hn of this one point space, then Hn of x, then relative homology, and then we have nh minus 1 of this one point space. So we know, so n is strictly greater than 1, so this means that this group, the homology of a point is trivial. This is trivial. This means that this map is necessarily trivial. This means that this map is also necessarily trivial. The only trivial map from or to the trivial group. And this implies, so whenever we have a situation of a short, in this, we now have a part of exact sequence which looks like this. So there's a pair of groups, and before we have a 0 and after we have 0, this necessarily always implies that this must be an isomorphism. So let me argue this in this case. So why this happens? So why is that? Okay, we know that the kernel of this map is the same as the image of this map, but this map is trivial. This means that the kernel is a whole space. Sorry, this means that the kernel is trivial. This means the kernel is trivial. This means this map is injective. On the other hand, this map is also trivial, and this means that the kernel of this map is the whole space here, but the kernel of this map should be the same as the image here of this map. This means that the image of this map is the whole space. It means that this map is surjective. So we show that this map is both injective and surjective. This means it's an isomorphism. Particularly here we have an isomorphism. So for n greater than 1, this homology group of topology group space X is the same as a homology space of X relative to some of its point, to its one point subspace. Okay, what happens? Now consider n equals let's see, 1 or 0, n equals 1. Equals 1. And so essentially consider the end of our long sequence. Okay, H1, one point space, H1 of X, H1 of X relative space, then continue to H0 of this one point space, then to H0 of X, to 0 relative. Then we finish necessarily 0. There is nothing. Okay, formally you can continue, but H minus h for negative degree is 0. You can formally, because there is no all these after that becomes trivial. Okay, good. So this is still the degree first. This is still 0, but this is now non-trivial. This is isomorphic to z. Okay, and let's see. So now we want to. So this map is still trivial. I want to argue that this map is injective. Why is that? So we kind of made a general statement before. We already made a general statement about this zero homology group. The zero homology group is given by the direct sum of path-connected components. So any space can be decomposed into a disjoint union of path-connected components. This is just the classes of points which can be connected by paths. This provides some equivalence relation. And for each path-connected component, we have a copy of Z. And here, so this is each copy of Z is represented, is generated by singular zero simplex, which so zero simplex is just a point. It's completely determined by its image. So it's generated by any singular zero simplex in the image in this whose image is inside this fixed path-connected component. Okay, and here, similarly, it's generated by some sigma, let's say sigma 0. Well, here there are only one non-trivial. There is only one map from one point space to one point space. And essentially, this means that this generator has not is here. You see that this generator is mapped to a generator to generator corresponding corresponding to the path-connected component, which contains this point, like 0. A class sigma 0 is mapped to a class, in this notation, mapped to class of sigma alpha, such that x alpha contains point. And this is definitely, so if a generator here is mapped to a generator here, there's no relation. This is a free abelian group. This in essence implies that this is injective. If this is injective, and we know that this sequence is exact, this means that the kernel, so the kernel is trivial. This means the image is trivial. So this means that the map here is 0. Okay. So if this map is 0, we again by the argument we already made, this implies that this should be isomorphism. And okay, and finally, okay, so this map is 0. This means this tells us that this must be surjective. So this surjective. This means that H0 is the image. Is the image of this map, and we can use the fundamental theorem to conclude that H0, this relative H0 of x comma x0, is isomorphic to the quotient of this group by the image of this map, which is injective, and the image is isomorphic to Z. Subgroup, this Z subgroup corresponding to a particular path-connected component of X, and Hn, and before, so we used for all other n's, we show that Hn, this relative homology group, is isomorphic to non-relative for n greater than
0. Professor, can you explain this first isomorphism between S0 relative homology and S0 X?
This?
Yes.
Okay. So in general, you have this fundamental. If you have a homomorphism from A to B, you always have some sort of phi. You have a statement that the image of phi is isomorphic to A quotient by the kernel of phi, right?
Okay, thank you.
Is this okay now?
Yes, it is clear.
Now, yeah. Here, yeah, just the image here is the image is a whole space because this is surjective, and the kernel is isomorphic to Z because this is injective. So this is an example how one can use this exactness to determine some groups in other groups. Okay, so any questions? Well, if not, that's it for today.